This is Hermann Kolbe, and in his day he was one of the top organic chemists in the world. But he's also responsible for one of my favorite science quotes of all time, which I cannot do with a German accent, so I'm just going to read it. It's kind of long, bear with me. Not long ago, I expressed the view that the lack of general education and of thorough training in chemistry was one of the causes of the deterioration of chemical research in Germany. Will anyone to whom my worries seem exaggerated please read, if he can, a recent memoir by Herr Van 't Hoff on the arrangement of atoms in space, a document crammed to the hilt with the outpourings of a childish fantasy. This Dr. J.H. Van 't Hoff, employed by the Veterinary College at Utrecht, has, so it seems, no taste for accurate chemical research. He finds it more convenient to mount his Pegasus, evidently taken from the stables at the Veterinary College, and to announce how, on his bold flight to Mount Parnassus, he saw the atoms arranged in space. Woo! Scorching! Now, you might be wondering if old Smuggy McSmugface over here ever had to eat those words. Oh, yes, he did. And that's part of what we're talking about today with VSEPR theory, where VSEPR theory is the valence shell electron pair repulsion theory. And it is the thing that allows us not to see the atoms arranged in space, but to predict their arrangement in space based on the principles of electrons repelling each other, like charges repel. Now, bonds contain electrons in pairs, always in pairs. We're going to refer to those as bonding pairs, or BP for short. And we also know that some central atoms have electrons also as pairs, just as lone pairs or non-bonding pairs. I'm going to refer to those as lone pairs, or LP for short. And those electrons are going to repel each other to be as far away from each other as possible in order to minimize repulsion. That is going to determine the overall shape of the molecule. We're not going to get into the background math or anything else like that, but we are going to be making use of the net result. Now, we have to understand that there is a hierarchy of repulsion strength, or differences in repulsion strength. So if I had two lone pairs, they're going to repel each other most strongly. If I have a bonding pair with a lone pair next, and then two bonding pairs will still repel each other, but not as strongly as the other two. Now, for the most part, that's not going to make a huge difference, but there are a couple of times when I am going to have to decide which location is it best to put a lone pair or a second lone pair, because I need to keep lone pairs and lone pairs as far away from each other as possible. And we also want to remember that an orbital is just where are we likely to find an electron. And what I mean by that is different forces that are involved in, or there are different forces involved in where am I going to find an electron pair. So it might seem like it's a good idea to find an electron pair here, but if there's repulsion forces on those electrons, they're going to go somewhere else. And for our purposes, we're going to treat a multiple bond as if it were kind of isn't there. We're going to treat, say, if it's got a double bond or a triple bond, we will count it as a single bonding unit. Okay, this table I think is really helpful. We're not going to be filling in any of the lone pairs today. That's a different time. But the number of bonding pairs, class, I don't really use that, but some people find it helpful. Shape, both the name of the shape and other information about it, I think is also worthwhile. I think it's important that you can visualize these things on a piece of paper, as much as it is that you can give a name for it. So we're going to start out with two bonding pairs, no lone pairs. AX2 just means that would be a generalized formula. The shape of that thing, well, if I get those things as far away from each other as possible, they're going to be 180 degrees away from each other, and that is going to be a straight line molecule, so it's going to be linear. I don't really need you to know the bonding angle, but it's not a bad idea to have it just for comparison purposes. If I had three bonding pairs and still no lone pairs, because that's another time, it's going to have that generalized formula, which again, I don't need that. It's going to look like that. In order to get those things as far away from each other as possible, they would all end up in sort of the same two-dimensional plane where they're 120 degrees apart from each other. So it would form the corners of an equilateral triangle. Not that we need that, but that would be what it is. And we're going to call that trigonal planar. Bond angles are 120 degrees. If I go to 4 bonding groups, now if you were to draw this on paper, it would end up looking kind of squarish or cross, up, down, left, right. But you have to remember that molecules exist in 3 dimensions. In order to get the maximum distance away from each other, I can make use of the 3 dimensions, and I end up with something where those bond angles are 109.5. Again, bond angle itself doesn't really matter all that much. I have this diagram here, the one closest to me, where I've got this wedge and a dash, and the wedge is trying to make it look like that chlorine atom is coming out of the screen towards you, and the dashed line of the chlorine atom is going back into the screen away from you. Not at, perfectly perpendicular or anything else like that, but coming out towards you and back away from you at a 109-degree bond angle. We'll talk about that notation another time. If you were to put the atoms, the bonded atoms, into the corners of a geometric shape, it would be a tetrahedron. It doesn't really matter, except that's where we get the name tetrahedral for the name of that molecular shape. 5 and 0. Now this one is always interesting to me because it's a combination, and there is not perfect symmetry. You have a system where some of the bonds are 90 degrees away from each other and some of the bonds are 120 degrees away from each other, and no matter how you did it, you're not going to get better than that. It's stuck in that asymmetric, that non-symmetric way of doing things. This is one where a lone pair has to, well, a choice has to be made. Choice is the wrong word. That is called a trigonal bipyramidal, because if you took the middle section, the 3 around the middle, and started drawing a shape out of it, it would be a pyramid on top and a pyramid on the bottom, so 2 pyramids, bipyramidal. 6 and no lone pairs is back to the symmetric thing, where we have, again, atoms coming out in 3 dimensions. All the bond angles here are going to be 90 degrees. And again, if you were to put those bonded atoms into a geometric shape, another one is at 90 degrees, missed that one, then it would form an octahedron, which gives us the name for octahedral. Now, take a second here and make sure that you understand that the octa, which feels like it should be an 8, that octahedral only has 6 bonded groups, but the name comes from the geometric shape that it would form. For things that we have to do some other time, we still have to figure out what happens with the lone pairs. We had a spot for that, but we didn't include any of them. How does that influence the name? How does that influence the shape? What about those ones where I said it matters where I put it? We still have to talk about double and triple bonds. I said we're going to treat them as a single bonding unit, which works, but why? What's going on with them that's so different? And then how does it happen? How do we get from our atomic theory, orbitals and so on, to make this stuff make sense? We have to connect those 2 things together. But this is where we're at as a starting point, and I think it's a pretty good place to be. Talk to you another time.